inviting me to speak at today's presentation, at today's conference rather. Let me just start by, obviously the focus here is going to be on structural geology, and I'm going to use, I suppose, research that we've been doing for the last few years down in Cork and UCC to give you, if you like, I suppose, an update on what our views are on the nature of the main deformation structures that we see across Munster, basically, the focus being on Munster. I'd just like to acknowledge my co-workers here, in particular, the second guy on this list, Jürgen Lang. This is Jürgen's, most of this work is Jürgen's PhD work. Jürgen was funded by ICRAG, so a shout out to ICRAG for the support for this work. And basically, and I'm glad to say that Jürgen has recently successfully defended his PhD, so well done to him for that. Let's just start with some very basic geology. Obviously, the Munster, we're focusing here on the Upper Devonian of Southern Ireland, and when we talk about the Upper Devonian, we're talking about the Munster Basin. So when we talk about the basin structure, the northern boundary of this basin, and it is an impressive basin. Depending on who you believe, there are people who argue that it's extending from Jingle Bay across to the Galties. I'm of the view that the dominant bounding structure is probably a little bit further south than what we're calling the Cumnacronia Killarney Mallow Fault system, which is this black boundary here at the northern end of the map. We have extending from, from 380 right the way through to, well, extension was ongoing right the way through to pretty much the end of the Carboniferous, but we have, in terms of the Devonian, the Upper Devonian, we have a significant accumulation of sediment. We don't see basement, and we don't see the base of the basin, but a minimum of 7, if not 8 kilometers depot center here in the southwest. So terrestrial, your typical, mostly fine-grained, medium to fine-grained red bed units, sandstone, siltstones, mudstones, etc. At the end of Devonian, we have the superimposition of, if you like, an intra-basin fault system. We're calling this the Cork-Kinmare fault, which is marked here in red. That divided the earlier basin into a region to the south of that, which we call the South Munster Basin. We're into the Carboniferous at this stage, widespread marine transgression. We see an accumulation over this period of, quite a thick siliciclastic sequence, marine siliciclastic sequence. To the north of that red boundary structure, we have a fairly stable carbonate platform. That continues up to pretty much the end of the Carboniferous, and then we have, at the end of the Carboniferous, we have the onset of a fundamental change in the, if you like, the dynamics of the system. We go from crustal extension to compression, and the onset of Variscan compression and deformation, roughly directed north-south or northwest-southeast. And the deformation sequence in general terms, we see a very early LPS, layer parallel shortening, or cleavage development, tectonic cleavage development. And this is really impressive in the south. And pretty much from a hydrogeology point of view, wiped out any primary porosity that was in these sediments. Ongoing compression, we see the development of folding, and we have that on all scales, at least 3 orders of folding. The first order large scale structures pretty much define the peninsulas that make up the southwest of the country, but we have hundreds of meter scale folding and meter scale folding as well, and I might come back to that later on. Then we have, traditionally, as what the view was, that this was very much a kind of a fold thrust belt. It's not really, and it's certainly not in the conventional thin skin tectonics view of the world. What we're seeing here is the inversion of an impressive basin fill sequence. So we get, at the late stage in deformation, high angle reactivation of bounding fault structures. And we're going to come back to those because these are particularly interesting for us and have been in what we've been looking at. We've got later cross-strike faults, which I'll talk about, and Sarah mentioned them earlier. And we've got, what I haven't spent a lot of time on here, we've got an impressive overprinting of jointing at the end of the deformation sequence. So one of the reasons we were looking at this was looking at copper mineralization, and I suppose this, in a way, is an excuse for us to explore in more detail the structure. The conventional view, I mean, Southwest Ireland, historically has been, a significant copper mining locality. Vein host, for the most part, vein hosted copper, and the view up to this prior to the start of this work is that we have, again, if you look down on the left-hand side here, we've got our early stage of our Pre-Variscan extension, the development of the Munster and South Munster basins, with compression and from kicking off at the end of the Carboniferous and the deformation sequence that I just outlined to you. And then we've got this late stage, if you like, post-orogenic or late orogenic extension that allowed the ascent of fluids, hot, highly saline fluids carrying copper and responsible for the mineralization. So we were going back, and there were a number of issues we've had with that and that sequence, and that was, I suppose, the primary driver for the research that we were doing. And we're going to, I think most of this talk, I'm going to focus on Allihies down here in the southwest of the country. So we're down here in the Beara Peninsula, for those of you who don't know it, we're right down here in the southwest of the country. And Allihies was one of, historically, probably the most important copper mining center, 19th century mining center in the southwest. We look at the local geology, and we're basically, this is the mine area here on the right-hand side. We've got two units, very, very typical of Allred Basin infill. So we're talking about Munster Basin infill here. The orange are what we call the Allihies sandstones, and these are medium to fine to medium grains sheeted sandstones. This is all terrestrial alluvial fan kind of material, and below that we have the Ballydonigan slates, much finer grain muds to fine silt grade unit. And the shaded area here are the lodes as they're described here, but these are large quartz vein systems that were the focus for the mineralization. Traditionally and historically, we've got the main mountain mine lode here at the boundary between these two units. We've got a north-south lode and an east-west lode above that, but we'll come back to that in a minute. So Jürgen was quite adept at using drone technology. So he did a very nice study, and he combined obviously kind of remote sensing using drones with obviously with ground truthing the structures as well. And I suppose to a great extent, that was the core activity of his research. And one of the first things that he picked up on was these very, very dominant east-west fault structures right across the mining area. Again, mountain mine, just from the point of view of spatially locating ourselves, is here in the south. So we're looking at the area immediately north of mountain mine in the Allihies area. If we superimpose the mineralized veins, so he carefully mapped out the main mineralized veins, and we can see that there is quite an intimate relationship between the orientation of these east-west structures, east-west fault structures, and the mineralized veins. Okay, and again, that was interesting to see. He then mapped in, and we're looking at this in terms of sequencing here. He mapped in a very dominant set of northeast southwest strike slip fault structures, Variscan fault structures, and you can see that there's quite a consistent sinister offset across these. Some of the earlier faults and vein systems have been offset in a number of localities across the area. So there was a nice, if you like, temporal chronology in terms of structure development. East-west structures early, and of course, we're hinting strongly here that these are actually basinal structures. These are extensional structures, followed by compression and these strike slip cross faults. When we look at these structures in the field, and this is a particularly nice example, when we look at the east-west structures and these two lovely conjugate pair here of faults, it became pretty obvious to us that we were looking at early features. This is the fault here. You can see, obviously, this sandstone bed offset showing a normal displacement. But what's interesting is you'll notice that you can see that the more complex sandstone that's impacting into the hanging wall and footwall here, showing that there was later compression. So these, to us, are very early extensional features. And we're arguing and have argued and have it published now that actually these dominant east-west structures are all basinal structures. When we look at the veins associated with these east-west structures, and again, you know, I've been working down here for many years, and sometimes you really miss the obvious. But when you look at these earlier veins, they're clearly deformed. The top two images there, the one on the left-hand side, is just showing you, and this is quartz. This is, you know, quite a large quartz vein that has been overprinted by a very, very penetrative, and that takes some doing, a very penetrative tectonic Variscan cleavage. You can see the same here on the right-hand side. You see lovely refraction of cleavage, exactly what you'd expect to see in terms of complementing contrast. In some places, in some of the larger east-west quartz lodes, using the mining term, we have brecciation. So these things were absolutely pulverized obviously during subsequent Variscan deformation. And actually, when you look at the vast majority of structures down in the southwest, particularly in the Alhis area, they are all these, and the quartz associated with them is all pre-Variscan. These are not Variscan quartz veins. These are basinal and extensional related quartz veins. We do, of course, see some classic Variscan structures. We have a lovely reef structure here, but you know, to be honest, they're pretty much few and far between, and they're not really an important component in terms of the vein history. This is lovely. This is, again, a lovely example of an early quartz vein that was folded and cleaved during the Variscan. We look at, just to give you an idea what these look like in the field on the left-hand side, and interestingly enough, when you look at these veins in the field, a lot of the sulfides and the, you know, the chalcopyrite and the other sulfides have been leached out. So there is little or no evidence that they're mineralized. We go underground, and we're lucky enough that in Alhis we can go underground. You see some lovely quartz veins hosting the copper sulfides. Just to show you a little bit of the kit that we've used in looking at more detail, this is Raman. We're lucky enough in Cork that we have a Raman microscope, and so we're able to do some mapping of, particularly looking at fabrics. And here, the black is quartz. There's quite a bit of albite in these, quite a bit of feldspar in these rocks, which is an interesting story in itself, and we can come back to that if you wish. But the black area here in the central part is a vein, and then we've got this yellow zone here of insolubles, basically, and these are basically fine-grained material that is defining a cleavage domain, cross-cutting the veins. So again, showing us that these veins were clearly deformed. And you know, like I said to you earlier, I've been working down here for quite a few years, more years than I care to admit. And this was this is actually my first paper that I ever published in structural geology. And you know, when I look at it, go back at it, and look at what I was talking about then, sometimes the truth is often in plain sight, and you miss it. You know, because I was looking at this particular vein here, very close to the mountain mine, literally within a couple of meters of the mountain mine. We've got early quartz development. Basin had to be basinal development and recognized as such. Subsequently deformed. We've got a second reopening event during Variscan, and that's probably due to folding and tangential longitudinal kind of stress and strain. And then we got this late lockup and subvertical opening. So we had that chronology back then, but we hadn't actually put that together in terms of an overall timing, and particularly a timing in relation to the copper mineralization. Now we do, down here, we look at the fluid inclusions and look at fluids, because obviously it's an important part of characterizing these quartz vein systems. For those of you who are not familiar with, this is just a simple plot, and we're looking at fluid inclusions. We looked at primary fluid inclusions, so these are little pockets of fluid trapped in the vein as the vein grew. They're at room temperature today, we're looking at their liquid vapor, their biphase, aqueous inclusions, highly saline. Look at here, just that's 38% sodium chloride equivalent. So these are at the top end here are brines and super brines. And then this is temperature of homogenization, and this is equivalent to, if you want to think about this as minimum trapping temperature. So these were quite hot fluids. And when we look, and saline fluids, and when we look at the early extensional veins, the deformed veins, this is the blue field here. We've got quite a range, and the really hypersaline fluids we're seeing in these early veins, which is interesting. The fluids in green here are what we are confident are true Variscan structures, vein structures, much tighter range. They're cooler and lower salinity. And again, bear in mind that during deformation, we've got dewatering is a big part of that for obvious reasons. And it's not surprising that we're seeing a dilution, if you like, and a overall relative cooling of fluids associated with Variscan deformation. I'm going to, Dave Selby and his group in Durham worked with Jürgen, and we got some renemosmium dates from those early veins, and we were delighted because, I mean, the structural story was pointing strongly at an early age for these. When we actually dated the stuff, we were coming in at 367, 366. I mean, this is bang on Sin extension, Munster Basin extension at that. So we were very happy with that. It was a nice confirmation of what the structure was telling us. So we had a total rethink, I suppose, and I'm not going to dwell too much on this. I'll come back to this slide again later, just to give it as an overview. But the key point here is that these east-west mineralized structures are actually basinal structures. So we're pushing back the time of mineralization back into, you know, the start of the Upper Devonian, and not the post-Variscan or late Variscan model that had been out there. Now, that's not to say that there weren't Variscan mineralizing events, and I'll show you an example of that in a minute. But certainly Allihies and some of the really bigger deposits, you know, were of that nature. And when you look at this map, and this was quite a bit of work that Jürgen did. He did kind of just a photogeology, kind of remotely sensed set of data. If you look at the dark blue here, these are these earlier east-west vein systems right across the southwest that make up you know, a large part of the fracture network, fault network that we're seeing down here. And we'll have a look at one or two more examples just to kind of, I suppose, back up and show, if nothing else, the consistency in what we were seeing here. So this is Gortavalig. Again, I'm not going to go too much into detail here, but again, your classic north, east, southwest structural trend, Variscan trend. This is one of these early veins, basinal veins, offset by a reverse high angle, reverse fault. Here, this is what it looks like in the field. This is an absolutely gorgeous example of a kind of profile of this high angle. And again, showing you, you know, these high angle structures, these are, you know, that dip close to, you know, 50, 60 degrees is clearly originally started off life as a normal structure. We've got a nice hanging wall fold structure here. Here we see one of these earlier Sin extensional basinal veins, if you like, cross-cut by the Variscan thrust. A lovely field relationship here that Jürgen spotted when he was down there. We look at this in again in more detail. This is obviously looking at the reflected light work on some of the ore minerals, and I think this is arsenopyrite and some chalcopyrite, and you just look at the highly fractured, almost brecciated nature of the material down here. So this is, you know, again showing us that this material underwent significant Variscan deformation. I'm going to scoot down to Crosshaven, right down here on the south coast, just to give you another example. Just to, I suppose, to show you the kind of the extent of this this timing and extent. These are fabulous, highly folded, deformed quartz veins. In this case, chalcopyrite bearing veins. And again, you can see that clearly they've been overprinted by Variscan cleavage and folding. Fluids, if we just look at, and this is from a few of the mines, again, you know, it's not as clear cut admittedly as before, but we are seeing, again, a shift towards the higher salinities in these earlier veins and lower salinities, cooler fluids associated. And this is from, you know, 5 or 6 of the kind of the bigger mines, other than Allihies, kind of, I suppose, supporting what we were saying earlier. We have a Mali date as well, and I kind of hinted at this before. We do have some true Variscan veining and structures, and we have some mineralization associated with it. So, you know, and we have a lovely, much younger dates, as you'd expect, 315, 311 there from the renemosmium and the Mali giving us that. So we had a lovely, if you like, you know, if you know, 2 phases of mineralization, this early basin extensional phase, and then obviously true risk material. Now, this may sound odd, but I'm going to hop out to Skellig Michael very, very quickly, because this is work Ken Higgs and I, quite a few people might know Ken, he's based here, he's retired actually, but he's doing still quite a bit of field work. And we remapped Skellig Michael over the last few years, and we've picked up 2 fault structures that are very, very similar to what I've just been talking about. And I thought it would be good to show you them, because while there's good exposure in Southwest Ireland, there's some really excellent exposure on Skellig. So I'm going to start with the Crosscove Fault, which is one of these basin extensional features. And here again, we see this is an actual shot of the Crosscove Fault. High angle dips. We see quite a bit of splays coming off the main structure, but not an awful lot of deformation around it. We managed to get the boatman to get into Crosscove. There's the fault plane here. We can see that there's quite a narrow zone of deformation, and it's actually quite ductile in nature. Now, bear in mind, if we're saying that these are early extensional, that type of behavior is not to be, we shouldn't be surprised. If we go and look at this other structure, which is this north-northwest, what we call the Blue Cove Fault, this is a late extensional fault. And this is on the southern side of the island, spectacular outcrop. Now look at this. This again, what I'm saying, this is late Variscan, okay? And it's accommodating a long strike extension during that late Variscan. And why that's happening, we can chat about later. But these are really, really impressive structures. And you can see, just to give you an idea of the scale here, that stick is a meter scale. We've got a fault core, highly brecciated fault core of over 1 meter. We've got a damage zone, the hanging wall, and a damage zone, the footwall, a combined damage zone width and fault core width of over, in some cases, 10 meters, highly fractured. So from the point of view of a permeability and a fracture permeability, these would be are impressive features and something to think about. You might say, why are we getting these late cross extension features? I mean, obviously, ongoing compression from the south, you'd expect east-west extension and late east-west extension after the whole system locks up. Also bear in mind, and I just threw this in here as a bit of a flight of fancy, but it is, Ireland sits on the in the northern flank, if you like, of the Cantabrian orocline, and I've been working with colleagues in Spain on this recently, and we're going to do more work. We would expect to, at this outer arc of the Cantabrian orocline, this is effectively the late orogenic bending and oroclinal bending of the orogenic edifice, and this occurred late in the deformation sequence, and we kind of, paleomag has established that is the case. So again, that outer arc extension that we expect up here would be and might be reflected in the structures that we're seeing. So basically, early extension, really, really important from the mineralization point of view. Then we've got onset of compression, significant LPS, folding, strike slip faulting, cross faulting, and what I haven't put in here, obviously, are these late along strike extensional faults and jointing, as a quick overview. So I'm going to leave the risk in there and just jump ahead, and I'm going to use my last few minutes, if I may, to talk a little bit about, and I only got a few slides here, about the DIG project. And I know Sarah has mentioned about our understanding of I suppose, the deeper structure and understanding of the deeper geology and its relation to geothermal energy. This is a project, it's led by DIAS, by Dougal, Kyan, Brian O'Reilly, and Chris Bean in DIAS. There's quite a group of people involved. John Weatherall and myself are kind of flying the flag for the UCC team. And this project, funded by, and I have to acknowledge, funded by SEAI, and greatly appreciated. Very quickly, we're looking at all scales, from an island scale approach, looking at things like the regional geothermal gradient, which I'm not going to speak about, but we're also looking at a more regional and local approach. And we've decided to focus in on Mallow down here in the south, because obviously this is traditionally an area where we've got warm springs, and quite interesting, and the possible, and this is where I come in, and John as well, where we're looking at the relationship of that to local structure. And this, and I have to give you a health warning about this, this is just data that's literally was shared with us this week, so it is just off the press. We did a preliminary magnetotelluric work, and I have to acknowledge the work of Tao Li in Dias, along with his colleagues for doing this work. And it's a profile, a magnetic telluric profile across the Clary-Mallow fault, which is the kind of the dominant, what I would argue is the dominant basal structure. And when we look at, again, this is, the team in Dias was said, please qualify this by saying this is very preliminary, because it is very preliminary. This is literally off the field laptop, as it were. But it's giving us an intriguing insight into the, I suppose, at depth, what's going on in terms of the Clary-Mallow fault. And again, this idea, because, you know, depending on who you're listening to and believe, this notion that we're dealing with kind of, you know, traditional, you know, truss tectonics or low angle tectonics is clearly not the case. We've got an almost vertical fault conductor zone here, significant structure, extending up to 7 to 8 kilometers depth. This is a minor fault, cross fault, and it's picking that up as well very, very nicely in the resistivity. So this is early work. We're literally just starting and we'll be doing the full surveys in the weeks and months ahead. But it's a very nice, if you like, teaser, I suppose, of what we're going to be doing down in Munster. Okay, I'm going to stop there. I'm not quite sure how we're doing on time. I think I'm not too bad, so I'll stop sharing.